Okay, moving on to chapter 3 in physics, we're looking at kinematics. Okay, so this is your velocity, speed, um, distance, displacement, acceleration. We're going to be kind of looking at that for chapters 3 and 4. 4 is specifically looking at um, acceleration. We're going to be looking at distance, displacement, and velocity here. Okay, so first, I'm going to talk about the difference between a scalar and a vector. So first, a scalar. So a scalar is something that just has one number. Okay, so it's like a weight, um, the battery output voltage, the volume of a bottle, a clock, measure of a weight of something. Okay, um, these all um, are represented by just a single number. Okay, what time is it? 3:45. How much does this weigh? 18 pounds. How much does this hold? 6 gallons. Okay. Those are just a single number. That's a scalar because you can increase the scale or decrease the scale up and down. Okay. So those are scalars. They're just represented by a single number and nothing else. Okay. So it's one number. Okay. Scalars again are just a single number. There's no direction to it. Okay. And again, another more examples that we have is how much do you weigh, your shoe size. On a scale of 1 to 10, how great is the movie Elf, which obviously is a 10. Uh, but again, a scalar basically has a scale of something. Okay, how far is it? It's 18 miles. Okay, that's a scale. Okay, your vector. Okay, okay, so vector. If we have something with a vector, we have a pair of Levi's, a bolt, a street intersection. All these have something in common. What are they? Are they represented by a single number or a string of numbers? And when we're thinking of pair of Levi's, we're thinking of a pair of men's Levi's. And these are all represented by a string of numbers. Okay, so numbers or words. So pair of Levi's, a men's pair of jeans is measured the inseam and the waist. Okay, there's two numbers. If you have a 3230 is your inseam and your waist. A bolt is measured both the length of it, so how long the bolt is, and how big the screw part is. So there's two. And then the street intersection, you've got two different streets. 12th and Vine is being descriptive on what it is. Okay, so these are vectors. So vectors, it basically carries some sort of location. Okay, so it's going to tell you more than just a number. It's going to tell you a location of something. So this would be an example of where we would have vectors. Joe is walking to the store. He goes 3 blocks north, 4 blocks east, and then another 2 blocks north. Okay. So what we have is we have vectors being formed. We're telling a distance and a direction. Okay. If we were just doing a scale, we'd just say, okay, Joe is walking to the store. It is 9 blocks away. That's all. If that's all we know, then that's all we know. We don't know which direction is he heading. Is he heading north, south, east, or west? Is it just a straight line? Is it where he has to zigzag like this one? A vector is going to be more descriptive on it. Okay. How far away is this town? It's 10 miles east. Okay, that's a vector. If you just say it's 10 miles, that's a scale. Okay, so a vector needs some sort of direction for it. Okay, so position. Some of this stuff is just kind of terms that we're going to be using that you'll need to know. So position. Position, whenever we use the word position, it's your starting point. It's your 0 point. It's where you originally start your journey, or you are referencing everything from. So this could be your desk, your home, school, Bojangles, New York City, wherever you're starting. Okay, that is your position, or wherever you want to be starting. Okay, that is what we consider your position. Okay, distance. So whenever we're talking about the word distance, we're talking about a scalar. Okay, distance is usually just a number. What's the distance from here to here? It's just going to be a number. 8 miles. So let's say we have this example. We have Tommy and Chucky are running away from Phil and Lil. They ran 10 feet towards the stairs, then 3 feet back before running back to the stairs another 5 feet. What was the distance that they ran? Well, the distance that they ran was just kind of the overall distance. So they went 10, then they went 3, then they went 5. So that means that they end up going 18 feet, okay, because you added up all of them, and that's their complete distance that they went, okay. The direction in which they headed did not matter. It's just the overall distance, okay. So in this case, it would be 18 feet. Now, displacement is different. Displacement is a vector, and it's the distance you've moved from your original position. So from your position, how far have you moved? Okay. So again, this is a vector, so you want a distance and a direction. So 34 miles east, 10 meters at 45 degrees northwest. Okay. They're going to give you a distance and a direction. 16 feet away from the desk. Okay, that's what you're going to have. So let's say we have the exact same example. So Tommy and Chucky again are running away from Phil and Lil. They ran 10 feet towards the stairs, 3 feet back before they ran another 5 feet towards the stairs. Okay, so with this one, if we're looking at displacement, what we have to do is we have to judge where's our reference point. Well, from where they started from. Okay, so from where they started, they ran 10 feet away from it. Then they ran 3 feet back. So now they're only 7 feet away. And then they ran another 5 feet. So in this case, their displacement would only be 12 feet, not 18. Okay, because they went backwards 3. So this one we would say that their displacement, or the distance they are, how far away from their original spot they are, is only 12 feet from it. So they're 12 feet from their original position. Okay, so that would be the displacement. Okay, so visualize it. So A, B, C, D, E. Suppose you're going along bike ride. You ride 1 hour at 5 miles per hour, then 3 hours at 4 miles per hour, and then 2 hours at 7. How many miles did you ride? Okay, so take a second and identify how far someone rode. And again, we're looking at distance here. Okay, so the answer to this one is 31. Okay, so the answer is 31 because what you would have to do is you'd have to find how far did you go each individual hour. For 1 hour, you rode 5 miles per hour, so after 1 hour, you went 5. Then 3 was at 4, so 3 times 4 is 12, so 5 plus 12 is 17. And then 2 at 7, which means you went 14 miles, so 17 plus 14 is 31. So again, that's what you're going to do. Reason you want to visualize it is because you can make a graph of it, and you can see, oh, okay, this is your speed, this is your speed. And then what you do is you'd find the area underneath each one. Okay, that's called a position. That's called a velocity time graph, which we go into more detail on those different types of graphs. So a dragster starts at rest and accelerates uniformly. So it's the same acceleration going across. It's going to be a straight line up to 60 miles per hour in 10 seconds. How far did he travel in those 10 seconds? Okay, so again, I would draw it, and then you want to find the area. Okay, so the distance that he traveled over those 10 seconds is 1/12 of a mile. And the reason why it's 1/12 of a mile is because we'd have to convert the 60 miles per hour into how far you would go every second. Okay, and then once you convert it into seconds, okay, so it ends up being 1 mile per minute, which means you're going 1/6 of a mile every second over 10 seconds. And so you would end up multiplying it through, and you find your area, which is 1/12 of a mile. Speed, distance, and time. So our connection between them. So the speed of an object is found by taking the distance and dividing it by the time. Okay, so um, that's the relationship. So speed or velocity is equal to d over t. Okay, and then once you have that formula, you can manipulate it to find different ones. So if it's speed is equal to distance over time, that means that distance is equal to speed times time, and time is equal to distance over speed. Okay, so you can take each one of those and you can manipulate the equations. So when we have speed, we usually measure it as a distance over time. So we'd say miles over hours, or meters over second, kilometers over days, etc., etc. So we usually have a distance divided by a time, which is from our formula itself. Okay, so back to the Rugrats. So again, same situation. We have our um, situation of them running back and forth. Let's say they did this in 10 seconds. Okay, so let's say they did all this in 10 seconds just to keep it nice and round. What would their speed be? So if they did it over 10 seconds, their speed would end up being 1.8 feet per second. And the reason is because we take our total distance traveled. Remember, speed is dealing with distance. Their total distance traveled, which is 18 feet, and we divide it by how long it takes. So 18 divided by 10 is 1.8. So it'd be 1.8 feet per second. Okay, so we want to keep those units. Now, velocity. So speed and velocity are similar, but they're different because velocity is our vector of it, which means that the displacement is used in it. So velocity deals with displacement, while speed deals with distance. Very confusing, but we need to know the difference. So velocity and displacement are our vectors, while speed and distance is our scalars. So what we would do with our velocity of an object would be taking the total displacement and dividing it by the time. And the same thing is still true with our meters per second and everything. The unit is still going to be the distance over that. So same situation with Tommy and Chucky and Phil and Lil. Let's say they do that entire thing over 10 seconds. So now ran 10, back 3, over 5, which means they ran 12 total meters. So they're, again, over 10 seconds. What would their velocity be? Their velocity would be 1.2 feet per second. Because, again, you take the displacement, which ends up being 12, and divide it by the total distance, which ends up being, or divided by the time, which ends up being 10 seconds in this case. Okay, so this graph right here is showing the speed of an object along the y-axis and the time along the x. Okay, so so look at this graph, and from this, can we tell how far away we are from the starting point that we ended up at? Okay, so A, it is impossible to tell because the graph has no numbers on it. Okay, B, it ends up at the starting point, or C, it did not end at the starting point, but where it ended up can't be told. So by looking at this graph, are you able to say where it is going to be located? Is it at the starting point? Could you give a rough estimate of where it's going to be? But you can't give exactly with the numbers. So take a second. Which one of these do you think the answer is? The answer to this one is B. It ends up in the starting point. So as you see, there's blocks. How many blocks are there above? So if speed is positive, or velocity is positive, so how many blocks are it in positive? There's 3. How many blocks are negative? 3. If you travel 3 miles north and then you went back 3 miles, you end up back at your starting point. So the displacement of this graph would end up being 0. It ends up back at the starting point. The distance traveled would end up being 6, though. Alright, so that's the end of this chapter, chapter 3, dealing with displacement and velocity. We're going to be moving on to acceleration next, which is a slightly longer section.